So next we're going to move to the Sensors tab. As we've established on the Acquisition tab, the spectral peaks, we have robust peak detection, we have wavelength tracking with the instrument. Now those spectral peaks are ready to be identified as FBGs and then used in computations as sensor elements. We did mention that in our real-world example that our sensors are a good distance away from our interrogation system, and so we're going to show you the tools to contend with those distance offsets. So we're going to enable compensation, we're going to verify that the refractive index of the optical fiber is set correctly, assign FBG distances, and then we're going to enable distance compensation on a per-channel basis for each one of those fibers. So back to our application. There's a global setting to use distance compensation on the Settings tab. In many cases, particularly when looking at relative strains in the absence of absolute temperatures, it is entirely acceptable and frequently convenient to ignore the effects of the speed of light offsets on the optical sensors and to simply establish a 0 point for a strain, zero that strain, and operate in a relative mode from there on out. So in many measurement situations, it's not necessary to set the distances. In our application, it is important because we've placed two absolute temperature sensors at a very far distance. The relationship between wavelength and temperature is a complex third-order polynomial, which is very sensitive to shifts in the wavelength. And so it's going to be critical that we establish the correct distance to those sensors before we apply the calibration expressions to the FBG so that we get the correct temperature information out of those sensors.
One thing I'd like to point out is, in a lot of cases, as Todd pointed out, it is convenient and simpler to ignore distance compensation. However, if you are operating at some distance away from the interrogator, particularly on the SM130, you will realize a better spec, a little bit better repeatability on the measurements by putting in the accurate distance, because the instrument is now distilling the wavelength fluctuations from the correct portion of the internal reference.
Yeah, so there are two reasons to use compensation. One is to, again, get absolute temperature data at a distance, and two is then to optimize your repeatability for any measurement, including relative strain sensors. So here we are in the Settings tab underneath the Application Settings. You see a Boolean control here to enable distance compensation, and that one checkbox will then activate different controls and data entry features through the remainder of the application on all the other tabs. The first place where it adds a control is here in the Acquisition tab. You can see under each of our channel controls that there's, underneath the gain to threshold, we now have a control for the index of refraction. And so, of course, the physical distance is of importance to our system, as is the optical path length. And the optical path length is going to be a product of that physical distance and the index of refraction. And so it's very important that we tell the system not only how far away physically is the sensor, but what's the refractive index of the fiber so that we know exactly the time of flight that's required to go from the interrogator to the optical sensor. In our case, we're using some standard single-mode fiber from Lucent Technologies, and it's a very well-published 1.4682 refractive index. And so those are the defaults that we have built inside the application, so we don't need to change that. We want to make sure that it's set to that for both channel 3, which is where we have our first fiber connected, and channel 4, which is where we're going to measure our absolute temperature sensors. Okay? And so now we're on the Sensors tab, and we want to create FBG elements out of our spectral peaks that we've found on our Acquisition tab. So I'm going to do that initially here with the Auto Create FBGs button. And what it's going to do is give us the option to create on multiple channels. So we'll go ahead and create FBG elements on channels 3 and 4. And then it's going to offer us some controls to establish the default minimum gap between those sensors and the minimum width of those FBG elements. And so we'll go with the defaults here. It's going to endeavor to put a 1 nanometer gap between the bins and create bin widths of 2 nanometers. Okay, and now we can see, and I'll go ahead and turn on the FBG limits for our display. We see that on channel 3 we have 5 FBG elements, which have been automatically named. Channel 3 is indicated by the C, so C for 3, D for 4, and then each of the FBGs is named in numerical order in which it was found in ascending wavelength order. Additionally, we can see that we have 2 FBG elements that were created on channel 4. And before we go to use these FBG elements to create sensor elements, we want to assign the correct fiber distance to each of those FBGs and then enable distance compensation. So I'm going to do that one by one here. I believe on our first fiber we were at a distance of 4,079 meters. And I'm going to apply that distance for each one of our optical FBG elements. Okay. Distance again of 4079. Okay. Now all 5 of our FBGs have a distance value assigned to them. And with those distances assigned, we can enable distance compensation. What this will do is we'll take into account the distance from the interrogator to the FBG, take into account the time of flight of that light from the time it leaves the interrogator, hits the FBG, and returns back to the interrogator, and then back that out of its calculation of the perceived wavelength of that sensor. So as I turn this on, what we should see is a shift of all of these FBGs. Right now the interrogator perceives the first FBG at 1531, but we know that to not actually be the case. That first FBG is by design a 1521, and they range up to 1542. So now by telling Nlight the distance at which those FBGs are stationed from the interrogator, and then enabling distance compensation, we're measuring the actual values of those FBGs unaffected by the distance between the interrogator and the FBGs themselves. And so we will do the same for our FBGs on our second fiber on channel 4, which in our example slide we had at a distance of 4,023 meters. Now I'm going to stop short of assigning the distance on the second one to point something out. Distance compensation is enabled on a per channel basis. So if we go back to channel 3, we notice that this icon is depressed and it's got a blue background. If we go to channel 4, it's not. So these are independent controls on a per channel basis. And if I attempt to enable distance compensation on a fiber where not all of the sensors have a distance assigned, in other words, that they don't all have a non-zero distance, Nlight will object and tell us that in order to use distance compensation, all of the distance have to be set to a non-zero value. This is basically to prevent any oversight and logging the distances so that we get a correct distance compensation. So again, these sensors are at 4,023 meters, and I'm going to enable distance compensation. And similarly, we see a shift here from their perceived measurements to the actual wavelengths. Okay? Move back over to our PowerPoint and make sure that we're covering our goals. Okay. So those were our 3 points for FBGs. Reviewing the questions here, there's a question, is distance and metric only? The answer is yes. The distances are to be entered in metric values, specifically in units of meters.